I'd just like to start by acknowledging and celebrating the first Australians on whose traditional lands we meet. And I think it's quite important when we talk about space. Some of the first scientists and space scientists, in fact, we have were the indigenous traditional people of this continent, and some of the exciting things they have. And so where I am currently in Canberra, I'm on Ngunnawal and Ngambri land. And so I pay respects to them and anywhere else where people may be attending from, and their elders past, present, and emerging. And so I will hand it over to the first speaker, and that will be Professor Russell Boyce from UNSW Canberra. Russ is the chair of Intelligent Space Systems and the director of UNSW Canberra Space. And he's going to be talking about smart satellites and really how it's important for what we're doing here in Australia, and some of the really cool things that Australia is doing in this field, like literally today and the past couple of months. It's a really exciting thing, and I'm sure you're all going to enjoy it. So I will hand it over to Russ.
Thank you, and thank you everybody for joining. It's a pleasure to be here. I'm going to spend about 10 minutes or so giving you some insight into the very exciting things that Australia is doing. We don't have to rely on the world as much as we used to in doing space, and there's some fantastic opportunities, including opportunities for you at home. So let's get into it. I'm going to share screen, and hopefully, can I have confirmation from somebody that we're good to go? Excellent. So on this screen, you see a number of images that capture what we are trying to do in my group, UNSW Canberra Space, but it's actually representative of the opportunity for Australia. And that is to not do space for the sake of space, even though space itself is cool, it's exciting, it's inspirational. The main reason that Australia is getting into space is to solve challenges and opportunities on the ground. And that's the intent behind these images here. Those spacecraft that you can see on the left, a CubeSat mission, which I'll describe a little bit more later in the talk, that my group are flying for the Royal Australian Air Force next year. But we don't just try to develop satellites and fly them. We did try to understand what are the problems on the ground, what can we put into orbit that can measure things, can create data, that can be turned into information to meet the needs of the person on the ground. We do it with the use of a particular form of satellite technology, a particular form of space technology that many have called disruptive space technology. I'm going to put it to you tonight that disruptive technology, CubeSats, it's no longer disruptive. It was about, let's say, 10 years ago, but things are changing. I'll explain why later, and I'll show you how Australia can actually disrupt that technology itself to create opportunities for ourselves. Why would we do space to solve problems on the ground? Well, Australia is very, very concerned with issues like emergency management, particularly the threat of bushfires. We're concerned with issues in the waters around our continent, and those issues might be the safety and security of the maritime shipping lanes that we rely upon, or it might be issues such as illegal fishing or people smuggling. We're concerned about the threats to our agriculture and our natural environment, and the opportunity for technologies such as precision agriculture. And we're also very, very concerned about the health of our maritime and freshwater systems. All of these and more can be solved through the application of space technologies. So my particular group, UNSW Canberra Space, formed about 5 years ago, pre-space agency. We could see opportunity to do exactly what I've been describing to you. We formed quickly. There's been quite a lot of money spent by UNSW and by the Commonwealth, particularly by the Royal Australian Air Force, and that's enabled us to bring Australians back from the global space sector. So we've been reversing the brain drain a little bit, and to bring other young talented people in and build the core of a capability to conceive and design and build and implement and operate space missions to meet those needs. One of the ways that we do that is right at the beginning in a facility that we call the Australian National Concurrent Design Facility. That picture that you can see on your screen just looks like a rather flashy room full of computers. It is a flashy room full of computers, but it's far more than that. Lurking underneath those computers, there's access to a server that contains software, which we were provided by the French space agency, CNES, in a partnership that enables us to develop space missions in Australia to the same world-class best practice as other folks around the world do, and to do it with a particular, very, very clever approach to design called concurrent engineering. In the old days, NASA or the European Space Agency or Lockheed Martin would have a requirement for a space mission, and one after another, the different engineers would get involved, and probably each one in turn would in some ways add some value, but also create some chaos to the contribution of those that came before them. And it takes quite a long time to do that, and it costs a lot of money. With concurrent engineering, you bring everybody that's relevant into the room together at the same time, including the customer. And you test the requirements, you analyze the mission, you design the spacecraft, at least to a conceptual level, on the fly, and it doesn't take very long. And very quickly you come out with an answer. Yes, this mission is feasible. It will meet scientific or the technical requirements or the national security requirements or the agriculture sector requirements, and it will cost this much and it will take this long. It's the only one of its kind in Australia, this facility, and it's a national asset that we have here in Canberra. And we use it quite often, and we'll be using it more and more into the future to meet Australian needs. So we start from there, and then we go all the way through into detailed design, and coming out the other end of that are the spacecraft themselves. What you can see in these images are glimpses into our rather modest clean room on our campus in Canberra. Typically, we also use the larger clean room facility and test facilities that the Australian National University has on Mount Stromlo, where Brad sits. But here on our campus, we have the smaller facilities where we do a lot of the assembly work for our satellites. Now, our satellites are not very big. That one that you can see on the left there, next to the gentleman in blue in the vertical photo, that's one of the two M2 satellites that will fly next year. You saw them on the very first slide. It's what we call a 6-unit CubeSat. This is a non-standard version of a 6-unit CubeSat, but it's about the size of a small book carton, and it weighs about 10 kilos. We'll be flying 2 of those in formation. More recently, we developed a mission called M2 Pathfinder in advance of M2 for next year. I'm very, very pleased to say, and some of you may have seen on the media, that M2 Pathfinder launched on a Rocket Lab launch in June of this year from New Zealand. It's safely in orbit, we're communicating with it, and pretty much every day we're making advances with the operation of that spacecraft, and it's creating flight heritage for almost 100% Australian designed and built space systems. That then is the precursor for the very complex M2 mission next year, where we add the payloads. So what's on M2 Pathfinder is what we call the satellite bus systems. Think of the bus literally like a bus that takes paying passengers to orbit. Well, in front of you, you can see contained in that 3-unit CubeSat, there are the bus systems such as the computer, the power system, the solar panels, the attitude control system, and other parts of the essential services for the mission. When we get to M2, we will be adding the payloads, which include sophisticated telescopes and radios to do some very, very interesting activities that I'll talk about a little bit later. I want to show you a short video clip.
9, 8, 7, 6, 5, 4, 3, 2, 1.
So Pathfinder launched successfully. Many of you would know quite a bit about the orbits of satellites, but many of you might not. So I'm showing this slide to give you a glimpse. Pathfinder is in what we call a sun-synchronous orbit in low Earth orbit. It's about 600 kilometres above the surface of the Earth and in almost a north-south orbit plane. And it does laps of the Earth about every 90 minutes, a little bit more than 90 minutes. It's travelling at 7.5 kilometres per second, which is really quite fast. So it's doing laps of the Earth in that north-south direction approximately. And every 90 minutes, it will pass over a certain part of the Earth, and 90 minutes later, we'll pass over it again, except that in that 90 minutes, the Earth has been rotating underneath it. And so on this next slide, I'm showing to you the orbit tracks that Pathfinder will follow tomorrow morning. At about 22 minutes past 5 tomorrow morning, it will come up from the south over the Antarctic. And when it gets to the start of that green track that you can see at 5:22, we will actually be able to see it from the ground in Canberra. We'll have line of sight. We'll be able to start talking to it with our radios. About 10 minutes later, it will disappear off our ability to talk to it to the north, somewhere around Papua New Guinea. So it's only 10 minutes to cover that enormous distance. About an hour and a half later, we do it all again. But by this time, the Earth has rotated. And instead of being out over the Tasman Sea, it's somewhere over the Great Australian Bight. That's tomorrow morning. Tomorrow evening, we get the reverse. We'll find that the Earth has completely rotated 12 hours. We're on the other side of the universe as far as this orbit is concerned. And now it will be coming from the north and heading south. And so at 10 past 4 tomorrow afternoon, it'll come down over Pacific islands such as Noumea. We'll start to be able to talk to it then. And then when it disappears off the south past Macquarie Island, we'll no longer be able to talk to it, and so on. When we're lucky and there's no cloud and rain, we can use a space surveillance telescope such as the one that we have at our campus to actually track this satellite and collect data from it. So that little dot you can see on that image is the satellite, and we're tracking it through time, and the streaks are actually stars passing by on the image as we move the telescope. So M2, I said to you that I'll give you a little glimpse into that. It's 2 satellites. They fly as one, as a 12-unit CubeSat. They'll be bolted together. And when we're ready in orbit, we will break them apart from each other, push them apart gently, and fly these 2 in formation. So it'll be the first time that Australia has ever done formation flying in orbit. On each one of those satellites, there will be a telescope capable of imaging objects on the surface of the Earth with 5-metre resolution. We're actually going after large ships. We're demonstrating for Air Force, in this case, possible capabilities in maritime surveillance. We also have on board radios at which we can tune to different frequencies, and that can be part of the surveillance capability. We have other experiments as well. In fact, we'll be able to talk from one satellite to the other. We'll be able to send information from one to the other and use them as a relay system. And we're even trying an experiment in doing optical communication between the 2 satellites. That's a stretch objective. We'll see how we go. I said at the very start that we're using space technology to try and meet needs on the ground, technology that people sometimes call disruptive technology, but I say it's not disruptive anymore. It's not disruptive anymore because about 10 years ago when it was disruptive, it was enabling a new group of users, particularly universities and even schools and small companies, to be able to access space, but they were doing it one small CubeSat at a time, and they weren't particularly useful. It was a disruptive market then, and the technology has been growing in capability. It's now what you might call a sustaining technology market, not disruptive anymore. Well, the new disruption is coming, and that's when you put lots of satellites into orbit, as some companies have started to do, but you network them to each other so they can all, in some way or another, talk to each other. And most importantly, you put onboard intelligence. So I'm going to flick to this next slide just to give a little bit of flavour to the talk. Satellites, almost entirely for the moment in orbit, they're not very smart. They have very, very sophisticated sensors, but they don't have very much capability to turn data into information. That is changing, and that's a significant part of the opportunity for Australia. It's a significant part of what we're doing in our group. And we can see a world where, if I go back to that previous slide, we have spacecraft, very inexpensive spacecraft in a global constellation that are not just intelligent each in their own right, but the entire constellation acts together as an intelligent organism, and it's able to quickly detect anomalies, detect changes, convert it into information, and get the information to the ground into the hands of the user who needs to make a decision in almost real time to help meet those needs and create opportunities for Australia and for the world. You might also imagine that you could take this technology further from the Earth, and we're hoping that one day that will be possible to assist Australia, in turn assist our international partners in planetary exploration opportunities. So I'm going to leave you on that slide again. This is the opportunity for Australia. It's about meeting the significant needs and the amazing opportunities that we have on the ground with the use of some really, really amazing space technology. Thank you, everybody.
Thanks a lot, Russ. We have a couple questions. So one from Al, how actually long did it take to make the satellite, to make M2 Pathfinder?
That's actually a very good question. M2 Pathfinder, we started that mission in April last year, and it took about 10 months to be ready to fly. And that's 10 months of start to finish development, design, build, integrated all together, testing, so that we were ready for launch and confident that we would get a good outcome. To our knowledge, that's the second fastest development time for a CubeSat ever. The company in the US known as Planet, which was co-founded by an Australian, Chris Boschhuizen, holds the record. This is to our understanding.
I mean, 10 months is pretty quick.
10 months is fast. However, let me share something with you. The previous mission that we flew, known as M1, failed. And that was a very, very significant moment for our team. And it's actually an important message for Australia and the way we go about doing space. Space is hard. M1 reached orbit and we were never able to talk to it. And to this day, we don't know why. But we took a very, very close scrutiny at what our processes and our the way we were testing, the way we were designing and building, even our culture in our team, and realised that in some ways we were still kids and we needed to grow up. And so we applied the lessons learned and got really rigorous really fast, and that enabled us to develop and fly M2 Pathfinder, assisted by the urgency because we needed the success and the heritage of Pathfinder in order to proceed to M2.
Great. And one question from Paula, how were the satellites launched into orbit? So I think you said this, but what launched them?
So Pathfinder was launched on a Rocket Lab Electron from the North Island of New Zealand. Rocket Lab is quite an amazing company. It's an American company, but it is now, but it started in New Zealand, and they lead the market for launching small spacecraft into orbit. There's other opportunities around the world, but Rocket Lab's an excellent example. Australia is starting to develop capability as well.
Great. Thank you very much. Russ, I will hand it over to the next speaker. And again, we'll have time to chat to everyone at the end. So Sinead King. So Sinead is one of our mechanical engineers and electrical engineers working on instrumentation up at Mount Jerome Observatory at the Advanced Instrumentation Technology Center. And she's going to talk about the fun someone gets to work on space electronics, and specifically a very cool project called EMU. And I'll hand it over to her.
Thanks so much, Brad. So let me just share my screen. Can you all see that okay?
Yep.
Yep. Okay, so as Brad mentioned, I'm an instrumentation engineer at Mount Stromlo. My talk tonight is on the challenges of space electronics. And I did have to adjust my title slightly after writing this talk because I realized that there are many challenges to this area of work. And I'm going to be talking about these challenges in the context of the EMU Space Telescope mission that I'm working on. So a little bit about me. I grew up very curious about how things worked, and I always wanted to know more about the universe. I was also quite creative and loved to solve hard problems. So when I was in about year 11 of high school, I decided that I wanted to do engineering. And I had this dream to build electronics for space and planetary exploration. So think of the Curiosity Mars rover, for example, and here's a photo of that down here if you don't know what that is. So I studied robotics engineering and computer science at ANU, and I graduated in 2014. I also did a bit of astrophysics in my early days there. And now I'm at Mount Stromlo and I'm working as a space instrumentation and test engineer as well. So what my job involves is basically building electronics and software for astronomy instruments both on the ground and in space. And I also help test satellites in preparation for launch at the National Space Test Facility, which is also located at Mount Stromlo. And here's a picture of one of the vacuum chambers that we have in that space test facility. So you might be asking, why do we want to put electronics in space at all? And what do I mean exactly by electronics? And we can take a simple definition just for this talk, and let's say that electronics are anything that rely on electrical power or batteries to operate. So things that you might find inside of your mobile phone, your computer or TV. And here I have a picture of a CubeSat that Russ was talking about before. So it's a shoebox-sized satellite, and it has a ton of electronics inside of it. And you might ask, why is it that we want all of these electronics? What do they help us do? And I think the biggest thing is that they help us communicate to our satellite. So once the satellite is launched and it's orbiting around Earth, we want to be able to send instructions up to it and get data back. Otherwise, it's just a piece of metal flying around the Earth and not really doing anything too useful. So by having, for example, radios on board, we're able to do this. So you can see here on this satellite, there's a couple of radio boards, as well as what's called a whip antenna. And when the satellite is put into space, these antennas kind of splay out and they're able to receive signals from Earth and also transmit signals back down to the ground. And of course, we need some kind of battery or power to those boards. Electronics also allow us to locate our satellite. So once they're in orbit, they might have some sensors on board, such as a magnetometer, which measures the magnetic field around the Earth, because this varies with how far you are away from the Earth. You might also have a GPS sensor, or something as complicated as what's called a star tracker, which is actually a camera that points out into space and looks at the different star constellations and can figure out by looking back to a database where it's actually pointing in space. Electronics also allow us to move our satellite. So once we know where it is, we might want to reorient it in a certain way, maybe to take photos or to communicate to a ground station. So some satellites might have propulsion systems or small thrusters on board, and we might have a control computer that can actually control those thrusters and move or reorient the satellite. Electronics also allow us to protect our satellite. So if we have processors and things on board, they can get very hot, and we want to be able to measure how hot or cold different parts of our satellite are, and turn on heaters or turn them off if we need to protect things from getting damaged. And I guess the most important thing is that they actually allow us to do useful stuff. So in case of the EMU mission that I'm working on, we have a space telescope that's taking images of stars for astronomy, but you can equally as well point your satellite down to Earth and take images of the Earth's surface. So over here, we can see a little camera sensor on the front of this satellite. I hope you can all see my mouse, by the way. Yeah, okay. And if we can have computer processors on board, that means we can also make our satellites a lot smarter. And this is what Russ was talking about before. So humans don't need to make decisions on behalf of the satellites. We can kind of leave them to their own devices and get things done much faster as well. So that means that we don't have to put humans into space, which is great because humans are a lot harder to keep happy than satellites. So I'll tell you a little bit more about the EMU space telescope that I'm working on. So this is what the instrument looks like. And it's not really a satellite on its own. We're actually hitching a ride on the International Space Station. So we're going to mount the instrument on the outside of the space station and point out into space. And as the space station drifts around the Earth, it actually doesn't go around the same orbit. So it eventually covers most points of the sky. And we can see that in this animation here, except for the North and South poles. So we're using this to our advantage. And we're able to use our instrument to take photos as the ISS goes around the Earth. And eventually we can build up a star map of the sky at infrared wavelengths. So we've got an infrared camera on our telescope, and this information can help astronomers figure out how these particular stars actually form. This down here is part of a simulation of the star map that we'll be generating. So you can see each of these spots is actually a star at infrared wavelengths. So that's kind of what our map's going to look like at the end. And the important thing is we can't actually do these measurements from the ground. And that's because the Earth's atmosphere actually blocks this infrared light from coming through because it has water, and water absorbs infrared light. So in terms of the parts of this instrument, we have the main telescope where the light actually comes through these holes and it bounces off this primary mirror where it's then reflected off this small secondary mirror at the front and down into this tube to where the infrared camera sits. We also need a cooler to make sure that the camera stays nice and cold, and a bunch of camera control boards, which is my area of work. And these are responsible for reading out images from the detector and from the camera and storing them to main memory. So we're going to be taking a lot of images to build this map of the sky, and we need about 60 terabytes of memory to be able to store all of them. And we also have a main control computer and a power supply in there as well. So why can't we just put electronics into space? What are the challenges there? The first challenge is that there's no air in space. So Earth actually attracts gas particles to create a thin atmosphere, which is why we can breathe. So that contains nitrogen, oxygen, and carbon dioxide. But space actually doesn't have anything to keep those particles there. So it's practically empty. There's no atoms there. When we make satellites on the ground and satellite materials like glues and electronic components and circuit boards, some of the gas particles in the air are actually trapped inside. And so when we go and put these satellites in space, what happens is these gas particles try and escape from these materials. So here we have a representation of these gas particles, these pink things here. And when we put it into space, what can happen is they can go and contaminate some of the sensitive parts of our instrument. For example, the mirrors of our telescope. And that means that the telescope can't function properly anymore. So this is a really big problem. So there are a few different solutions to this. One is that we can put everything in what's called an airtight box. So it actually has air inside of it. So this is what we're doing for the memory portion of our design. But this will leak over time, so it's not perfect. And it does mean that we can't actually get access to those components of our instrument very easily. So it's not that practical to work with. We can also use what are called low outgassing materials, which have controlled manufacturing processes so that they don't trap as much of these gas particles inside of them when they're being made. But they can be slightly more expensive. One of the other solutions is to actually clean your satellite by cooking it or using a process called bake out. And what this means is that you get your satellite and you put it inside of a vacuum chamber, which is what they're doing in this photo here. And you actually heat up your satellite. And inside the vacuum chamber is a thing called a cold trap. Now, when you heat the satellite up, those contaminants are released and sucked into this cold trap. So you've essentially cleaned your satellite. The second challenge I'm going to talk about is temperature. So temperatures in space are very extreme. They can range from thousands of degrees right down to near absolute zero. And the problem is most electronics have to stay between about -40 degrees to 85 degrees Celsius. So we can see over here, if the ISS is on this side of the Earth, then it's going to get the direct sunlight on it and get very hot. But if it's on the other side, our instrument is going to get very cold. So one way of combating this is using what's called MLI, which is this gold reflective material. And you may have seen it on many different spacecraft. And this effectively reflects the solar light that's hitting the instrument, so it reflects it away and also helps to stabilize the temperature on the inside of the instrument. So it's basically slowing down these extreme temperature changes. If we have processors on board, for example, you may have seen inside your computer that they have fans on top of them to keep them nice and cool. Well, we can't actually use these in space, and that's because there's no air, as I mentioned before. So fans need air to actually suck in and carry the heat away. And that means that we have to rely on conduction and radiation to transfer heat. So here we have a processor chip. Some of the heat is radiated out into the vacuum of space, but we have to get most of it out using conduction by having a metal plate in contact with that processor chip. So that's what we're doing on EMU. In fact, the whole base plate of this instrument is connected to a temperature control plate on the space station. And that's what actually sucks the heat out of our space telescope. The third challenge I'm going to talk about is radiation. So space is filled with radiation, and this is high energy particles which come from the sun's solar wind. And we can see an artist's depiction of what that looks like. It also comes from distant galaxies and supernova events. Now, Earth is quite protected by its magnetic field, so we're pretty safe down on the ground, but satellites aren't protected. And what happens is the radiation actually comes in and can tear through the spacecraft and satellites. And that causes the materials to degrade, and it also upsets a lot of the electronics and scrambles any data that you might have on board. So some of the solutions around this are using radiation shields, so thick pieces of metal. Obviously, they're very heavy and they don't stop all the radiation, so it's still a problem. You can also use special space-grade materials and devices that don't get upset by radiation, but these are extremely expensive and usually only used by large space agencies like NASA and ESA for very long duration and deep space missions, where radiation is going to be a really big problem. So what we're doing for EMU is we're using everyday commercial components that we know work well enough for our mission, and our mission's only going to be about 6 months long. And we're also using a number of careful design techniques on the circuit boards, like multiple copies of circuits and software. So if one breaks, we have a few backups. And we also have a few unscrambling and reboot mechanisms. So if anything goes wrong, we can kind of repower our system and restore everything. Okay, so I've just gone through 3 of the major challenges, but there are many, many others which I don't have time to touch on. But what we can conclude from this is, as Russ pointed out before, space is really hard. So how do we know that once we've done all these things, our satellite's actually going to work? Well, we can't be sure, but we can get pretty close. And we do this by testing our satellite or parts of our satellite using space simulation facilities like the National Space Test Facility at Mount Stromlo. And this has a vacuum chamber called the Wombat XL thermal vacuum chamber. And we put our satellites inside of there and suck out all of the air. And then the internal surface of that chamber, we can actually control the temperature to get really hot or really cold. And we make sure that our satellite inside still functions. Another facility that we have is the vibration and shock facility, which allows us to mimic rocket launch vibrations. So here we can see part of the EMU cooler being vibrated to make sure that it doesn't break. And we also, on main campus, have this particle accelerator facility, which allows us to generate radiation to do radiation tests. And if our satellite passes all of these tests, we can consider that it's ready to be launched. So hopefully you've learned something about the challenges of designing space electronics. I just wanted to leave you with this image, which I think epitomizes very well the challenges of working in the space industry as an engineer. So thanks very much, and happy to answer any questions that you might have.
Sorry, I'm laughing. You had a great series of graphics at the end there. So a question, and I think you may have touched on this, but I just to be clear. So what's the life expectancy of EMU?
So the mission duration will be about 6 months, and that'll allow us to get that kind of full map of the sky.
And what's the limitation on the 6 months? Is it space in the ISS or?
It's probably more the memory, the onboard memory that we have to have, because we have to take so many images. We already need 60 terabytes of memory, which is really kind of pushing the limits. And the reason for that is because we can't send it down to the ground fast enough. So we have to be able to store it, and then eventually we're going to bring just the memory portion of the instrument back down to the ground so that we can process the data.
Yeah, and that just relates exactly to someone's asking, how do you essentially gather the information in return? So literally just moving this data physically back.
Yes, we will be kind of trickling down some of the data as the mission is ongoing, just so that we can do some kind of early processing on it and make sure that everything looks as it should.
Yeah. So this is part of your fun, I guess, is you hope that it all works smoothly, right? Because obviously if you lose 6 months of data, that would be sad for everyone.
Exactly. But I think, as Ross pointed out, it's all a huge learning experience, even if something goes wrong. So
yeah. No, I think that's right. I mean, it's something you both touched on quite well. It's even in the failures, as rough as they are, you learn something, I think, and improve. So that's exciting. So, I mean, it's great to hear we may have soon an Australian space telescope. That's kind of wild.
Yeah, and this is actually one of 2 that I'm working on. So the same camera technology that's going in EMU is also going in another space telescope mission called Skyhopper, and ANU is working with the University of Melbourne on that. And that's another infrared space telescope that's actually going to be twice as big. So it's a 12U satellite, independent of the space station.
Yes. That's awesome. Well, thank you very much. I'll pass on to our next speaker. And again, we'll have time to dive just more, because there's a lot going on. And so Dr. Amy Parker, so she's based at CSIRO in the Center for Earth Observations. So her job is working on operating Novastar 1, which was Australia's first observation satellite, I think. Amy will correct me if I'm wrong, of course, because I'm usually wrong. And so you get to hear kind of, the next continuing phase. We're talking about how to build it and get there and make it work. And then making sure we can all get it to work in space. Now it's actually operating in space. So Amy, take it away.
Thanks, Brad. And happy Science Week, everyone. I hope that some people in the audience participated in the Satellite Selfie with Maxar this week. So can I just check you can see my screen? Okay.
Yep, I'll look at
yeah,
it.
Awesome. So today I am going to talk to you a little bit about some of CSIRO's activities with Earth observation satellites. So as Brad mentioned, I work in the CSIRO Centre for Earth Observation, and CSIRO is Australia's national science agency for those of you who aren't so familiar with it. And at CSIRO, I am a satellite operations and data manager. So I'm going to take you through some of our activities. Starting with a little bit of a background on Earth observation. So Earth observation from space basically involves using satellites that host different types of sensors, as Russ has mentioned already today. And these take images of Earth's land, oceans, and atmosphere. And some of these rely on sunlight to illuminate the Earth, and they create images using visible light. And others send out their own source of energy to illuminate the Earth, which means that they can see at night and they can see in different types of weather. And we use these Earth observation satellites every day. They help us to provide weather forecasts, detect oil spills, bushfires, to map melting glaciers, to monitor the growth of crops, and to assess our urban environments. So pretty much every aspect of life you can think of, they are helping us in some way. And in Australia, we're one of the world's largest users of Earth observation data. But as has already been mentioned, we don't really have a history of operating and using our own satellites. Instead, we really rely heavily upon international data providers. So things are starting to change, and we've heard a bit about CubeSats already today. And principally, satellites are becoming smaller and cheaper. So we've gone from these large rhino-sized satellites that cost billions of dollars down to CubeSats that are, the size of a loaf of bread, or as the Canadian Space Agency have chosen, a duck. And these cost hundreds of thousands of dollars instead. And of course, these smaller satellites can't always do all of the same things as those multi-billion-dollar satellites, but they do provide some new opportunities for countries like Australia to change the way that we use Earth observation satellites and to establish some of our own sovereign capabilities. So at CSIRO, we've long been experts in downstream uses of Earth observation data. And when we talk about downstream, that's really where we get that data already on Earth from the satellite, and we then analyze it and use it to create new ways of mapping crops, new ways of looking at different parts of the environment. We create data tools. And our Earth observation, the Earth observation activities that we are involved with really cover about 80 different scientists that work across all sorts of different aspects of our science, from looking at mineral mapping, to looking at energy resources, to looking at our land and waters. And all of that is really coordinated by the CSIRO Centre for Earth Observation. What we're starting to do now is to look more at the upstream side of Earth observation, particularly the development of sensors that are put on the satellites, and also looking at how we can actually process some of the imagery on board the satellite before it reaches Earth. And this is really cool because it really reduces the volume of data that we then have to send back down to Earth, which is kind of a bottleneck when we think about how much imagery we can get from space. We can collect a lot of it, but then we struggle to get all of that information back down to Earth. And then we're also working on operating our two different satellite capabilities, CSIRO-Sat1 and Novasat1, which I'll talk to you a bit more about. So CSIRO-Sat1 is our first CubeSat, so we're very excited about it, and it's due for launch next year. And it's been built in partnership with an Aussie company called Innovol, who are based in Adelaide. And then what we've done is to design the onboard sensor, and this is what we call a shortwave infrared imager. And then, as I mentioned, we've also been looking at how we can perform some onboard data processing on the satellite. So kind of a simple example of this would be to have an algorithm onboard the satellite that looks at the image, and if the image is covered by clouds, so we can't use it for the purpose we want, it wouldn't send that image back down to Earth. And that's kind of a simple example of onboard data processing. So the shortwave infrared imager that's on board has a number of different potential applications, and we're talking with our scientists to see how they might use the data, because that obviously then helps us to design the mission. So I just mentioned to you that if the images are covered by clouds, we might not want them, but if actually we want to use this sensor to look at clouds, then those are the very images that we might be interested in. Some other options are looking at different types of land cover, so discriminating between urban areas, crops and bare ground, or even detecting radiative heat from bushfires. So our second satellite capability, and the one that I'm quite heavily involved in, is called Novasar-1. And this is a satellite that is owned and operated by a company in the UK called SSTL. And CSIRO, on behalf of Australia, are part of what we call a mission partnership. And that involves the UK, India, Australia, and the Philippines. And that partnership allows us to operate 10% of the satellite's acquisition capacity. So we can plan and task imagery anywhere on Earth, but we have priority over the imagery that covers Australia. And what we can also do, which is really kind of a first for our country, is to send that data that's collected from the satellite directly to ground stations, so satellite antennas that are in Australia. And that means that we can access the data faster than we could before. So what does Novasar do? So the sensor on board is what we call a synthetic aperture radar. And this is one of the sensors that doesn't rely on the sun, but it actually transmits its own source of electromagnetic energy to Earth. This then bounces off objects on the ground and it scatters that energy back to the satellite where it's recorded. And because it's what we call an active remote sensor, it means we can operate in all weathers, day or night, and we can see through smoke and clouds. So that synthetic aperture radar on board Novasar is also unique because it's the only one that's in space that's operating in the S-band part of the electromagnetic spectrum. And that really means that it sees the Earth differently to other SAR satellites, which is really interesting from a science perspective and is something that we are going to be exploiting. And then there is also another sensor on board that can detect certain types of radio signals from ships. So similar to the CubeSats that Russ talked about, it has potential applications for monitoring shipping activities. So what's exciting about Novasar is that CSIRO will be operating it as what we call a national facility for research. And this means that all of the data that's collected will be available free and open access. It also means that researchers will be able to submit proposals so that we task imaging over their areas of interest. And that national facility will open later this year. In the longer term, we are really interested in using Novasar as a possible pathfinder towards a full-scale national satellite constellation. And the benefits of participating in this mission partnership are not just that new science that comes out of it, but also that it allows us to gain experience in planning a satellite acquisition strategy, in operating and in tasking satellites. So I'll quickly take you through kind of a basic overview of how we go about actually making that mission plan and taking that imagery that we're interested in for our science projects. So the first step is to access the orbits, and these come from NORAD, or the North American Aerospace Defense Command, and it shows you where the satellite's going to be at a given time. So these are the passes of Novasar over a given 24-hour period. The next step is then to define an AOI, an area of interest. And these come from our research and development projects. So in this case, we're interested in looking at some imagery over Sydney. They can come from disaster events, so covering bushfires, or they can simply provide background imagery of the country that we can use to then refer back to at a later date. Finally, we then see where those orbits and where those areas of interest intersect and see whether we can use that particular image capture in the mission plan. Does it clash with any other requests? Do we have enough capacity on the satellite to actually take the image? So the white boxes that you can see appearing on your screen show you where we've been collecting Novasar data over the last year. And you can really see that since December, we've been ramping up operations and collecting a lot more data. And actually, since we started collecting data, we've now captured over 700 images. And the majority of these are over Australia, but you can also see there are some areas in the oceans and also over New Zealand and some of the Pacific Islands. So in this early phase of operations, we're really interested in developing some basic case studies from the Novasar data. And there are a couple of examples of this on your screen now. So the first has been to look at mapping damage from the January and February bushfire season. So this is an area of New South Wales, and you can see the areas that have been affected, shown in green and red. We've also been looking at a flood event that occurred in the Fitzroy River in WA in March. And again, you can see the extent of the flood waters mapped in the different colours there. And then we were able to capture some data over the White Island eruption that occurred in New Zealand at the end of last year. So to quickly recap, what we're really doing is supporting up and downstream Earth observation activities. And this goes from the design and operation of sensors on board satellites to developing new tools for looking at Earth observation data, there's always more and more and more Earth observation data. So we need to find new ways of actually dealing with this huge volume of imagery that we now have access to. Australia is gaining some satellite capabilities, and we've heard a bit about this from a number of speakers today. And for us at CSIRO, this is our CubeSat CSIRO Sat1 due for launch next year, and then Novasar 1, which we're launching as a national facility. So we do also have opportunities for undergraduate students to join us in the summer vacation to help out with some of these activities and get involved. And there's lots more information about those vacation scholarships available on the website. And we would be looking for students to apply for next summer as the applications for this year have now closed. And then if you want to find out more information about our Earth observation activities, about CSIRO Sat1, or how to access Novasar data, more information can be found on our website, or you are welcome to send me an email. Thanks, Brad.
Thank you. So someone's asked, again, kind of related, what is the lifetime or lifespan of Novasar 1?
Novasar is a 7-year lifespan.
Okay.
Yeah, so it's actually quite a reasonable time frame.
So it has good lifespan still to go in it, which is always good. Yeah. And so who's responsible for keeping the satellite in position? Like, so obviously you have to do some corrections. So how does that all work?
Yeah, so it's this kind of an introduction to operating a satellite. So all of the, what we call the TT&C and all of those kind of commands and operations are overseen by the company based in the UK, SSTL. And then we are in charge of planning our data and submitting those plans to the mission operator, and then actually organizing our downlinks. So ensuring that the data that we have essentially ordered from the satellite comes back down to Earth.
Okay, cool. Well, thank you very much. So again, we'll have time to discuss amongst everyone at the end. Just want to leave plenty of time for that. So our final speaker is Dr. Fang Yuan, who is at Geoscience Australia currently, in the assistant director of the product development in Digital Earth Australia. Her background comes from PhD in physics, and after that working on explosions in the universe with me, actually, as a close collaborator and colleague. So now she's doing something less explosive, hopefully. So I will hand it over to Fang.
Thank you, Brad. I'll share my screen. And is it working?
All good.
Oh, good. So I know why I'm the last speaker now. So I'm not actually going to talk too much about satellite themselves, but I promise there will be lots of pretty pictures to look at. So as Brett said, I currently work at Geoscience Australia. So we're a Commonwealth Science Advisory Agency. We're located in southeast of Canberra. So if you're driving off Hindmarsh Drive, you might be able to see this big building right next to the road. If you've visited Geoscience Australia before, we have a really nice rock collection in the foyer, including a rock from the moon now. But there are a range of other sciences we do that's not rock related, including study of the Earth's surface in more recent history or currently. And there are also a number of space-related projects. For example, we do operate a grant receiving station, and there's also a positioning program that helps to improve the accuracy of positioning from satellite systems. So what the program I'm working in and I'll be talking about today is Digital Earth Australia. So in a nutshell, what we do is take satellite observations or data from satellite operators, apply additional corrections if required, and put them in a nice and easy to access format, and then run analysis on them, so that we get derived information from these satellite images that can help a range of industry that can be used by governments for decision making. So this is the only slide that I will have pictures of satellite or models of satellite showing. I'm really glad that the previous speakers have explained a little bit how satellites operate and how they orbit around the Earth. So the two series of satellite we mainly rely on are expensive international satellites. One is the Landsat series and the other is Sentinel from Europe. So all these satellites are in sun-synchronized orbit, orbiting around the Earth at about 700 kilometers above the Earth's surface. And this is, I believe, where the selfie is taken this week as well. So there's one of these, so this is how the orbit looks like. So why do we need these expensive satellites? Is because they cover, every time they go around, they actually cover really wide swaths, so that they can cover the entire Earth every couple of days. So we get repeated imagery over Australia. And one of these satellites in this slide uses synthetic aperture radar, as Amy just described, but I'll focus more on the satellites using optical sensors. And the other great thing about these is that these large programs provide all their data open and free to use for everyone. So as I said, what we want is a repeated coverage of the entire Australia, so that we can monitor change, which means there is a trade-off, but not so much of a compromise, because this is an example of the image that we have over Canberra, and you can actually still see a lot of details. Although if you zoom in on Geoscience Australia building, you can roughly see the shape of the building, but not so much as you can see in the Google satellite images. So you will not be able to count cars in the parking lot, but you can see enough to tell where the artificial surfaces are, where there are buildings, and where there's vegetation covered. And still, every few days, because we cover the entire Australia, so we still have billions of pixels that we have to deal with. And the other thing that was also mentioned is that, so these are optical satellites. So if you look at an image taken in visible light, if you combine 3 images taken roughly at the wavelengths of blue, green, and red light, you can see the Earth's surface, but the color looks kind of dark. It's a little bit hard to tell where are trees and where are the bare surfaces, and the water bodies have very different colors. But if you also take observations in the infrared, and not just near infrared, but shortwave infrared, which is much longer wavelengths than the visible light, you can combine these images in different ways that actually allows you to tell much easily where different kind of land covers are. And in this particular example, all water bodies show up as dark or blue color, so that you can very easily map them. So I'll take this example forward. So, which means that if we map all the water occurrence across Australia over time, we can produce maps like this that gives us some idea of how often water is observed at every place in Australia in over 30 years. So this kind of information is obviously fairly useful because we can learn about the water distribution across Australia. And actually, if you see so at this resolution, you can't really see a lot of permanent water body at all. Most of the water bodies you can see are the salt lakes and floodplains that are flooded only a fraction of a time in a year, or sometimes only wet less than once every year. But I have to show this, which is what we are a lot familiar with. So this is a picture of, well, Lake George, how the water occurrence changes over years. This was actually made a few years back, so I think it's probably due for an update, as I heard that Lake George has water again. And we can basically track this over time. And if we do this for all the water bodies that are big enough across Australia, we're able to map at any certain time how full these water bodies are. And this is just a snapshot showing that sometime in 2019, Australia is actually very, very dry. So most of the water bodies are showing up here as red or orange. So they're less than 10% full. So this is actually giving us a sense of how dry the country is, and a way to map drought. So similarly, we can also map vegetation and bare soil. So this is just an example of fraction of green vegetations for the entire country, or fraction of bare soil, and we can track this information across many, many years, and so map the changes from year to year. So this is work in progress. Again, you recognize Canberra. So this is just an example of the change between 2 years. So what's highlighted here in pink red is where development has happened, and so the vegetation cover has reduced, and the green bits are where the vegetation cover has increased. As you can easily tell, some development happens in the northern Canberra region. So as mentioned before, this gives us a way to track things like drought, but we can also map flood if it lasts long enough. Since Aperture radar is a great technology that complements this because they can see through clouds, so we can actually map flood more effectively during the raining events themselves. But with the images we have, we can map the flood extent regularly without having to do special analysis. And the other thing we can map is the impact of fire. So although we can't see the fire directly at the time, we are able to tell the burned area after the event by mapping the change of the vegetation and the ground cover. And since the beginning of this year, what I have been involved in is a team that's establishing Digital Earth Africa. So we're basically taking the technology that we've developed for Australia, but applying it to a continent that's 4 times as big, and also have 50 countries. So the challenges that we're dealing with are very different, and we're working with people in Africa very closely to make sure that the technology and the applications we build are actually useful for them. And as you can imagine, water and food are 2 of the main challenges they're facing. So using the same technology as how we map water in Australia, this is just an example in an area in Tanzania. So across 2 years, we can see that on the left-hand side, it's a relatively wet year. So you can see the big lake that's almost always full throughout the year. But on the right-hand side, it's a relatively dry year. So the water body is actually dry most of the time throughout the year. And the other challenge we're really hoping that we can help is food security. So this is just another image for an area near Cape Town in South Africa. So as you can see on the left-hand side, this is observations taken in visible light. You can see the vegetation's change, but on the right-hand side, this is using the near-infrared information so that the photosynthetic vegetation are highlighted and very clearly discernible from the other type of ground covers. So use these kind of information. We're hoping that we can map where crops have been planted and harvested across the year, and consequently to help monitor the growth and health of the crops. And last but not the least, I've shown lots of pretty pictures, but in reality, we're having thousands of images every day. So we're not going to look through every images ourselves. I spent most of the time sitting in front of the computer and getting computer to do all the work. And these and the data, the amount of data we now have petabytes of data. So we need big computers, such as the National Computational Infrastructure on the ANU campus or the Amazon Cloud Service to host these data and also process them to get information out of them. And once we have derived information from them, all the data are shared back and made public again. So these are hosted either at NCI or AWS again. So that can be accessed by researchers or industry to put applications and use them in more different cases. And the other place that we share data is the national map. So you're able to go to the national map portal and see a lot of the information products and satellite imagery that we have. And this is also where the satellite selfie is going to be shared. So I will stop there. Thank you.
Yeah, thank you very much. You're right. Satellite selfie will be there. For those of you who've been in Canberra, we'll get the weather sorted. Don't worry. I don't know how, but I will. Or my skills. The Northern Territory has been clear, as Fang Yuan showed. The Northern Territory is pretty dry and reflective. Digital Africa, that's really cool. How did that come about? Was it something that groups of organizations in Africa came to Geoscience Australia, or you realizing you can apply your skill sets and data techniques elsewhere? So a little bit. Can you offer a little bit more about it?
So that's partly because of the success of the Digital Earth Australia program. And actually, the technology behind it is called Open Data Cube. So there's a big international community, and CSIRO is part of the Open Data Cube consortium. And we have groups around the world that work with us using the same technology. And so it's a recognized one. The Digital Earth Africa program is funded for 3 years by the Department of Foreign Affairs of Australia, but also partly by a not-for-profit trust fund in the US.
Cool. That's really awesome. Yeah. So we have a few minutes before we're going to end. So if anyone has any questions that we haven't really answered or talked about, please submit them now. I was going to ask one to all four of you. Obviously, you've talked quite a lot about a few different things and how quickly it's changed, right? Rusty started talking about disruptive technology 10 years ago, and we can kind of look where we are today. So, predicting the future, what are the exciting or big things, or the things that you think are going to be even more transformative on the radar in the next 5 to 10 years? So, what are we talking about when we do this thing in 2023, which hopefully doesn't run like 2020? Russ, you want to have a go?
Sure. Thanks, Brad. So I mentioned, and in fact, many of our speakers mentioned putting artificial intelligence into orbit. And I think that is going to be a very, very big thing that happens. It's going to happen quite quickly. It's probably going to take a few years before we get good at it. But the opportunities that are going to come from that are significant. But there's some other things that Australia does extremely well, which we can put into orbit as well. And that's quantum technologies. Australia is amongst the world's lead at quantum computing, at quantum communications, which is basically unhackable, secure communications, and also quantum precision sensing. There's some amazing capabilities that are being developed in our universities and labs around Australia. And if you couple that to space technology and put them into orbit, enormous opportunity is going to come. And that's an example of a niche area that Australia could be a world leader in.
Yeah, that's kind of a good point, because you've kind of hit on a couple of different points of not just, for all of you, not just building the technology and perfecting it, but then how are we accessing it? What are we doing with it? Who's using it? And how do we have other people using it? I think, yeah, that's quite cool. Amy, any thoughts on this?
From kind of the downstream Earth observation perspective, definitely we're dealing with an increasing volume problem. It's how do we get the data to Earth, and then once it gets here, how do we deal with this amount of data? How do we store it? How do we extract the value from it? So we have things like the Open Data Cube, which is kind of a way of actually organizing all of this information. And one of the things that we're really interested in at the moment is then how do you integrate these different data sets together? How do you put radar data with information from optical sensors? How do you integrate that with LiDAR? How do you then incorporate hyperspectral data? So I think that kind of the analysis that we're doing with Earth observation data is pretty much being pushed to its limits as it is. And I would be expecting to see some really interesting kind of analytics capabilities, being applied to Earth observation data, perhaps bringing things in from astronomy even, and seeing how they can cross over into the Earth observation realm.
No, that's quite interesting. Fang, any thoughts on this?
So as everything takes a long time, I think what will be happening in 5 to 10 years is probably has to already been started now. And what I would be really excited to see, and I think we are already starting to do, is make these satellite images really easily accessible by a lot of people and used. And as Amy said as well, I think the next step is hopefully a lot more satellites data are going to be made easy to use, so that they can be combined, and with the advancement of the cloud technology, the computers are getting so much faster now and powerful, so that there are a lot more different ways we can deal with large amount of data sets and combine them.
That's actually quite a good point, right? The things that are now going to be mainstream in 5 to 10 years are the things pottering around the lab and the area in that early, disruption phase almost, Russ, that you talked about. Sinead, thoughts on that? What do you see, kind of the tinkering in the lab now that is going to be the working thing in 5 to 10 years, at least, maybe even on the electronics instrumentation side?
Yeah, well, I was actually going to take a little bit of a different stride with this, and say that I think the biggest thing for Australia that's coming the next 5 to 10 years is the Artemis program and the Moon to Mars program that the Australian Space Agency is collaborating with NASA on. So that's going to bring $150 million to the Australian space industry, which I think is very much needed. And it's going to be something that's really going to allow the industry to flourish and take off and, really try some new and innovative things, and hopefully build up the local expertise in space. I think in terms of satellites for that, optical communications is going to be a really important aspect. Because if we're going to establish a base on the moon, we're going to need good communications and high bandwidth communications. So that's something that ANU is working a lot on. And yeah, definitely a critical piece of technology.
Yeah, that's a great point. And Russ, I know when someone asks a question, you answer that, where the funding from these projects are coming from. And I think, as you both have identified, having that space agency now as a bit of a way to do some of these fundings and bigger projects is quite exciting. And someone's asked, and this is kind of related, I'm going to open this to anyone. What are your thoughts on the increasing commercialization of some of these things in space? SpaceX's Starlink, Amazon Kuiper. and how this may impact the future, because it's definitely different than it was 10 years ago, and the capability and funding streams. I'll open that up to anyone.
Maybe if I throw something in, for most of the history of the space sector, there's been only a few players, and they've been government players with a lot of money, like the US. And their space technology has been provided for the most part by a few very, very big companies, but working for government. This has changed completely, and most of the satellites in orbit are now developed and owned by the commercial sector for commercial outcomes, and it's only going to get more. Most of the use of space these days is around developing information for meeting commercial needs, business intelligence, for example, communications needs. The list goes. The list could go forever, but it's the commercial sector more and more is dominating.
And so you think that's a way of getting other people who would normally be pushed out of the market because they weren't one of these big players?
Absolutely, and that's part of the definition of disruption. It's when new players can start to offer a service that the traditional big players kind of overlook, and they offer it to new customers. And I think the world's waking up, certainly Australia's waking up. Space touches absolutely everything that we do on the ground. Space-derived information and communication capabilities, it literally affects everything that we do. And if you get creative, and the youngsters out there are so creative these days, and in the future, the not too distant future, they will be coming up with ideas to make use of this space-derived information, which is just going to boggle the mind. Enormous opportunities.
Interesting. Yeah. And so Caleb has asked, and this is kind of related to what you and Sinead touched on, and maybe Sinead, you can answer this first, and then anyone else, for that 150 million for Artemis, kind of, any idea where it's going? And I think specifically from Caleb's point, how can engineers be involved in this to be part of this, this revolution?
I know that the space agency was actually kind of touring around and putting it out to industry and research institutions as to how they feel they can contribute to the Artemis program. I know there's been a lot of talk, as I said, about laser communications and also space mining, like remote mining operations, because that's something that Australia's already really good at. So I think that's kind of where they intend the money to kind of go, but really I think it is open if people feel like they have a good idea. Yeah, so definitely, if you have a good idea, I think contact the space agency, because they're asking, people for their insight.
Can I throw something in on top of that?
Yeah, of course.
So the $150 million is roughly being divided into three chunks, 50 million each. The first one is going to be for the supply chain program. That's direct opportunity for Australian small companies, big companies, who may have nothing to do with space at the moment, but they're able to develop ideas which could in turn be of use to the international supply, or the supply chains of international space efforts, which could be the big companies, or it could be agencies like NASA and the European Space Agency. So that's the first big chunk, and it does have a lot of openings for all sorts of players across Australia.
Yeah, I mean, I think that's really great. It's because there is this excitement now and this buzz, both with all of you that you're seeing and what you're talking about, that, the next 10 years is probably going to be very different than the 10 years we've just gone through in this sector. And Keith asked a question, and this is, I guess, really at Fang and Amy, with all the work that you're talking about with CSIRO and Geoscience Australia, is anything happening in Antarctica? I guess, and the Australian Antarctic Territory, if we're counting that as part of Australia?
So at Geoscience Australia, we actually have a team works on Antarctica. So we are starting to work with them to see if we can use satellite observation to monitor, for example, the snow cover. yeah, so we're definitely starting to look into that.
And similarly, certainly in our kind of oceans and atmospheres division, there are scientists working in on Antarctican projects. And I've showed in my presentation some of the imagery from Novasar that we've been collecting there. And we've also been collecting imagery over some of Australia's very, very tiny, very remote outlying islands that are generally missed off the acquisition strategies of the big satellites. So hoping to be able to, make some interesting observations in some of our other, outlying islands as well.
The forgotten places.
Yes.
The other territories not on the map. Yes. All right. The ones that have natural travel restrictions. Look, I know we're a bit over time, and I'm going to ask one last question that's been floating around. You all obviously do really different and interesting things, which they're all great. I don't take much effort to get excited, but I'm even more excited. What is the most interesting thing about what you're working on? And related to that, what would you say to any students in the audience about what they may be thinking about doing in the future, advice, ideas, thoughts, inspiration? Amy, you're still on screen. I'll pick on you first.
Sure. So space is so far reaching. I mean, I started life as a geophysicist looking at, what's beneath our feet rather than thinking about space. But I'd say that's one thing that's really kind of key to all of us, I'm sure, has been the ability to work with numbers and the ability to work with software. So really kind of programming skills and math skills, I think, are kind of the fundamental keys to working in a lot of different aspects across the space sector. And beyond that, you could be a geographer, you could be, a physicist, but really the key languages are kind of numbers and then, computing languages. So that's a pretty good place to start. And then I think you can figure the rest of it out as you go.
I like that. Sinead?
So, I mean, I guess I just love solving really hard problems. So I think, working on electronics on the ground is kind of hard enough, but then putting it in space is a whole nother level. So, I mean, I just really love the challenge, and I love that I'm working towards something that, is kind of like a sci-fi novel in a sense, and it's going to get more and more like that with the Moon to Mars and human space exploration. And that's something that, I'm really passionate about. So it's great to be able to contribute in my own way. And I think it's important for the students interested in space to figure out kind of what their niche is going to be. And obviously, focus on getting that fundamental knowledge behind you in that particular area, but also spread out and kind of like talk to as many people as you can early on. So when I was going through high school, I actually went to a thing called the Australian Youth Aerospace Forum. And I think it's actually been renamed now to Aerospace Futures or something like that.
I think so, yeah, but similar, yeah.
Yeah, but I would say those sort of events are invaluable because you start building a network with people that have similar interests to you, and so many opportunities can come up from that. So definitely, don't think you're too young to start getting involved in that sort of thing. And I think those opportunities are a lot more prevalent now with, the whole space agency thing going on. So yeah, keep an eye out and get involved as early as you can.
Great. Russ?
Well, segueing from what Sinead just said, some people in Australia know, but probably not most. At the beginning of next year, we're actually hosting the world's largest space research conference. It's called COSPAR, and until COVID hit, it was going to be about 3,000 people face to face. Well, that's had to change, but there's actually opportunity for many, many more than that to gather, a virtual sense. Part of what we're doing, and I have the honour and the privilege of actually leading that conference. It'll be in Sydney. Part of what we're doing is a really, really big STEM push. There's going to be a face-to-face and virtual experience for school kids and for their teachers to get involved and go on a space journey with us. So if you want to jot this down, cosbar2021.org, and you'll get some information about how to get involved there. That's a plug for what's happening next year. But I'd also like to say, just in general, space, as I mentioned before, it touches everything, and it's very, very complex. It's very, very inspirational, but the best thing about it for me is it forces you to think critically and to be able to solve problems. You can't be involved in space if you can't solve problems. My advice to anybody out there who wants to get into the space game, study what you're passionate about, do it in a way where you're forced not just to take on board information and dish it back out again. Learn how to think. Any degree program that teaches you how to think can lead you into an area where you can get a space-related job. It could be in engineering, it could be in science, it could be in ethics, it could be in law, it could be in any of the ways in which information from space touches us on the ground. It could be something super cool like planetary exploration, but there's so many opportunities. It's all about being able to think.
Yeah, I really like that. It is almost what you touch on, Amy. It's getting just that practical skill sets and that mindset, and there's lots of ways of getting at it. And following someone who's gone from explosions to Earth observations, that hits to a good point. Wrapping it up here, what are your thoughts on this?
Yeah, so exactly as you said, I switched field, but I find myself using my knowledge of physics and maths and statistics and programming skills every day. All the technologies have a lot in common, and I've worked with telescopes in remote places as well. So that also has a lot in common with dealing with technologies in space. So yeah, definitely, as everyone has already alluded to, the fundamental skills that you need to acquire are important for a lot of different technologies. But there's also a range of careers, I guess, you can pursue related to space. The other thing I find myself enjoy a lot, both in astronomy and my current project, is that I actually really enjoy working with the people, because all the people I've worked with are very passionate about what they do, and that's actually really, really great bunch of people to work with as well. And I find the communication skills that I've learned throughout my years as an astronomer, being able to work with people in teams and with people in different teams, across teams, that are also very important as well.
That's I think an amazing point to end on, is that it's not done by any one person, but right groups of teams working on, from your videos you showed, but all the people analyzing the data and trying to solve the problems in the clean room. Thank you very much to all four of you. Look, I always have fun on these things. I had a lot of fun tonight. Thank you all to those of you who tuned in. Have a good evening. Wherever you are, and as I said, this will be recorded. I'll put it online and send a message out wherever it is to watch it again. So thank you, and take care.